Welcome to a video on first order filters. We will use these in our higher order filters when we have an odd number or an odd order filter. So we will be looking at inverting and non-inverting configurations for the low pass and then for the high pass, and lastly I will show you in simulations what's happening. Okay, so the inverting low pass filter. So I've gone ahead and designed all 6 of the filters in this document for 1 kHz and 20 decibel passband gain, or a 10 volt per volt gain. Right, so the inverting configuration, first of all, the output will be inverted. And sometimes you do not want the inverted output in your filter network. Okay, so this can be an issue depending on your application. The second nice thing is you can select the input impedance for this filter. Remember that this will be affected by the gain bandwidth product of your amplifier. Okay, so the gain bandwidth product will mess around with our cutoff rates or our stop band of our amplifier. And since this is first order, we have a minus 20 decibels per decade cutoff rate for this particular filter. Right, so in general, this is not a very good configuration to use. Right, the second one is a non-inverting configuration. I'm first going to say that this is a common mistake where people will convert the inverting configuration directly to a non-inverting configuration. Okay, so we will get to that in a moment. So first off, the gain is 1 plus the resistor ratio. We have infinite input impedance, but the problem is when we are not at cutoff yet, current will move through that resistor right there, giving us a gain. Then when we start to reach cutoff, we have both of these components active. But at some point, more current will pass through the capacitor than the resistor, and this capacitor will look like a short, making this a buffer circuit. So we will have passband gain, cut off, and then 0 dBs out. So if you need to boost a certain section of a signal or a certain range of frequencies, but the rest you only want to pass through your filter without affecting them, then you can use this configuration. But yeah, so this is a bit of a common mistake for building a non-inverting low pass filter. Right, so the actual or best way to do this, first you will have more components, is to build your non-inverting amplifier and then add a passive filter in front of it. Okay, so filtering will happen here with resistor 3 and capacitor, and the gain will happen with resistor 1 and resistor 2. Okay, so input impedance still remains infinite. Our output is not inverted. And one thing to note, at the transition frequency of the op amp, our cutoff rate will increase to minus 40 decibels per decade from minus 20 decibels per decade. Okay, so we will have a higher cutoff rate after a time. So whenever you see this in a simulation, it is due to the op amp's cutoff frequency. Right. Now for the high pass filter, so this is the inverting configuration, so output will be turned around. Again, we have a selectable input impedance. The filtering is dependent on these two components and the gain on R1 and R2. And again, this is dependent on the gain bandwidth product of our amplifier. So all high pass filters using op amps after a time will look like band pass filters because we will have our high pass effect, and then later on the op amp will start to cut off and we will have a low pass effect again. Right. As I was going through this, you might have noticed that I'm using strange component values. I'm using E24 values, not E12s. And for filter designs, go and download yourself a table with all the resistor values in, and I would say preferably up to E192 values. Okay, and in a design you always choose a capacitor first. There is more resistor values available than capacitor values. So choosing the cap first will make your life easier. Right. Now, again, the common mistake first, taking the amplifier and just converting it to a non-inverting configuration. Yes, we now have infinite input impedance, but the problem is for a time before we reach our corner frequency, this capacitor will not conduct. Okay, so therefore this resistor is not there. So this amplifier will act like a buffer again until we reach our corner frequency, and then it will start to work like a proper non-inverting amplifier. So again, the best method, passive filter, active amplifier, and that is again more components, but we have infinite input impedance and we can do our design separately. And remember again that this will become a band pass filter due to the gain bandwidth product of the op amp itself. So if you have issues at higher frequencies, select an op amp with a higher gain bandwidth product, and always try to keep the gain in your systems low for higher frequencies. And if you should have a high amount of gain, cascade amplifiers with a lower gain configuration that will increase the bandwidth. Okay, so let's jump over to the simulations and let me show you the response of each of these amplifiers. So I went ahead and built all three and a buffer for comparison so that we can compare them against one another. So let's run this, and for the buffer we can see that we have passband up until, what's this, looks like almost 10 megahertz that we are reaching right here. Right, okay, so the buffer output 0 dBs. So if we take this first one right here, we have our passband gain at 20 decibels, our corner frequency at 1 kilohertz. It will cut off nicely, and when we approach our amplifier's cutoff right here, it will typically flatten right here. Okay, so this is a bit of a problem for our inverting configuration. Right, second one, our non-inverting configuration. that was straightforward converted from the inverting, you can see that it follows this line right here. It will cut off for a decade because the gain is 10, so it will cut off for a decade, and then at 0 decibels it will continue on this line up until the the amplifiers cut off and then go down again. So if you want to boost a certain part of a signal and let a certain part just pass through, you can use this configuration right here. Okay, so the ideal one for the non-inverting, we have our pass band, we have our cut off, and it will cut off nicely until we reach our amplifiers cut off, and it will cut off much quicker. Right. So if I enlarge this, you can see that a bit better, that here at 100 megahertz we suddenly have an increase in the cutoff rate. Okay, so let's put all 4 here on the same. So our buffer, our inverting, our non-inverting as a mistake one, and then lastly, or the best option would be the non-inverting, which uses the passive filter configuration. Right, let's jump over to the high pass filters. So again, I set up all 4. Let's run this and compare them. So there is our buffer, and here is our inverting configuration. You see it will have our cutoff frequency here up until 1 kilohertz, and then we have our pass band, and then at 1 megahertz it will start cutting off again because these ideal op amps from LT Spice, their gain bandwidth product is at 10 megahertz, so this move to 1 mega. So we will have this cut off rate and then pass band, and it will cut off again. Right, the second option is right here. So comparing with a buffer, we will have 0 dBs until we reach our, or move toward our corner frequency. So we will have this cut off right here, pass band of 20, and then again cut off of a low pass effect due to the op amp itself. Okay, so if you have high gains and you see this behavior right here, it's your operational amplifier. Okay, lastly, the passive filter. So with the active amplifier, we have roughly the same as the inverting configuration right here. And there you have it. There is all 4 of our amplifiers compared. So yeah, I hope this helps in selecting a first order filter, or help solve issues if you solve them. And we will be using these in our higher order filters for the odd numbers. So yeah, thank you for watching, and see you in a next video.